Morning, everyone. We'll start this fourth day of the school with Pietro giving his third lecture on black hole thermodynamics.
Thank you. Okay, so today, Tuesday, I briefly reviewed, very fast, some kinematic argument for why you should think that when you are in presence of a Killing horizon, Lorentzian field theory in presence of a Killing horizon gives rise to a natural definition of a temperature, in the sense that an observer near a Killing horizon that follows the orbits of the Killing vector generating the horizon will measure a temperature on the detector that she has in her hand. And then, in a whirlwind account, at the very last 5 minutes, I showed that by an analogy, you can also measure this temperature just by looking at a Euclidean geometry that is smooth and includes a capping off of your space-time, where the smoothness condition, which avoids the presence of a conical singularity, requires the identification of an angle with a period generically different from 2 pi, and the period is identified with the inverse of the temperature. Today, I'm going to forget all the Lorentzian, and I'm just going to look at Euclidean spacetimes and see in practice, in an explicit example, how this arises and what is the procedure that you need to do in order to measure this temperature and construct the smooth spacetime. I will do this in the framework of the gravitational path integral, which is a way of quantizing gravity in a sense. That was suggested by Gibbons and Hawking in 1977 or 76, and I will do this not exactly as Hawking and Gibbons did, because I will do this in anti-de Sitter spacetime, and I will try to motivate why it's a better setup to work in. Yes, so this, together with the Lorentzian arguments that I mentioned on Tuesday, will give us a consistent picture of thermal setups in gravity. Stop me at any time if you have questions, as in the previous lectures. So, in fact, I'm going to start with a review of the path integral in quantum mechanics, because that's where we start from. So, the Feynman's idea, which is the path integral, just for this first few boards, there will be h bar not to 1, because then I take h bar to 0, and so I would like it to be present to see where it hides. So the idea of Feynman was that in order to compute the probability amplitude that a particle at position x1 after a time t is at position x2, is to actually sum over all the paths between x1 and x2, each weighted by the action computed on the path, where S is the action 0t or x of S. Okay, and dx is some measure that I'm not going to specify right now, but it's some measure that in fact can be constructed. So this is a little bit vague because S is real, so this integral oscillates, so it doesn't really converge. However, you can make this into a well-defined, mathematically rigorous statement if you take the Wick rotation of this statement, so of this construction. So we take t is equal to minus ITE, and the statement is that, sorry, we call it minus I beta h bar, and then we are measuring x2 e to the minus beta h x1, and the statement is that this object, which really is the density matrix, is given by the integral from x1 to x is equal to x1, x is equal to x2 of dx e to the minus se divided by h bar, where se is the Euclidean action. Here it doesn't really make sense of Euclidean Lorentzian, but it's a form of Euclidean action. Te is by definition beta h bar. Okay, so this formula, which can be constructed in a rigorous way, is the Feynman-Katz formula. And it tells you about actual probabilistic processes, stochastic processes that take place between x1 and x2. But now I would like to just show how you go from here to here, or vice versa, from S to SE. So why is this really just a Wick rotation in time? So we start from this one, and now we introduce t is equal to minus, then this is simply the integral from 0 to minus ITE. Let's write these everywhere. Yes. Now I introduce s is equal to minus ISE. So it's the integral from, from 0 to TE of minus m over 2 dx dsc squared minus v of x, because this doesn't change, minus I dsc. So I've simply changed variable twice. First I've defined a new endpoint of my integration. So I've analytically continued the path of integral, and then I've changed variables so that everything was real. But you'll notice that this is precisely SC that I had defined earlier. Minus. So what I've done, I've connected the probability amplitude with a density matrix formulation. So I've changed from a probability amplitude to a thermal system, because that's what the density matrix is measuring. And I've also claimed, this I've not showed, that this density matrix formulation is actually well defined. So once we do, now I'm going to end wave, but once we do the Wick rotation, in a sense, we're going to something better defined. And the reason for this later on will be that it's from hyperbolic we go to elliptic partial differential equations, and basically that's also the reason underlining here. Okay, finally, there is one last thing that we want to say about quantum mechanics, which is the fact that the density matrix is at the root of what I defined earlier on Tuesday to be the partition function of the system on a thermal state, in a thermal state, which is just a trace of the unnormalized density matrix. But what does it mean to trace something defined using the path integral? It means that I have to identify x1 and x2. So really this is the integral over all circles of length beta, because beta is, by definition, the length of the circle, of dx e to the minus se. Okay, so you'll notice that this is precisely what we have done the other day. We started from a system. Now let's move to higher dimension. Imagine that we are in higher dimension. We started from a system, Lorentzian, well, a physical system, that was defined, there were computed probability amplitudes here. Then we said that if we do a Wick rotation and we identify the path with an S1, so if we introduce a circle of length beta in our system, then we are really measuring the thermal behavior of this of the original system at a temperature beta is equal to 1 over T, at a temperature that is the inverse of beta, which is precisely what I'm doing here. Okay? Questions about this? Sorry, perhaps it was a little bit too trivial, but now I'm going to do exactly the same thing with with gravity, which is completely not defined. Nothing of this is defined, whereas here it's all rigorous and you can formulate everything. So now I'm going to define the gravitational path integral. So we take our inspiration from this type of computations, or field theory computations that are analogous to this, and we state that the probability amplitude for the evolution from a space-like surface where I have a metric G1, some field configurations phi1, and a topology sigma 1, to a space-like surface G2 with a field configuration phi2 with a topology sigma 2. So but notice that I can have a change in topology from one to the other. Then this object is measured by this, where this is computed over all the metrics G and all the field configurations phi and all the manifolds M that fill this time-like tube between the two. So time goes in the upward direction. You will say, you should say, that this is a garbage, as the French, in the sense that I don't know how to define any of these. There is no rigorous definition of any of these. But this we take as a framework, nowadays, we take it as a framework to understand what should the quantum gravity look like, or at least how can we think of quantum gravity. Quantum gravity, in this sense, this quantization of gravity, consists in the sum over all the space-time configurations between two boundary conditions. This hints, in a powerful way, and to an idea of quantum gravity as holographic, which is consistent with what we said what I said at the very end of Tuesday's lecture about the fact that the behavior of gravity is fixed by the boundary surrounding our system. Sorry, here is the Euclideanization of the action for gravity. Okay? So, let me tell you some details. So what I'm going to do now is to actually do a computation in this, with this gravitational path integral. And then tomorrow, I'll tell you everything that was wrong about this computation. So today it's optimistic, and tomorrow it's a day. Okay, so first thing, what is the Euclidean action that I should use? You'll remember that the Einstein-Hilbert action in Lorentzian has this form, where lambda is the cosmological constant, R is the Ricci scalar of the metric G. there is an immediate problem with using this action on spaces of this form that perhaps you're familiar with, in case I'll review it, is the fact that when you take the variation of the Einstein-Hilbert action to derive the equations of motion, you get some factor of 1/16. RJB plus lambda JB but then you also get a boundary term where H is the induced metric on the boundary, and NA is the normal to the boundary. And XA is some vector that depends on the metric and its variation. This is because perhaps you've seen this, that when I take the variation in order to get the Einstein's equation of motion, I need to also vary the Christoffel symbol. Well, when I vary R, I get something plus something exact, something that is a total derivative. This total derivative is then I use a divergence theorem and I throw everything at the boundary. But this means that the variation of this is technically given by this term. However, in order to make the Dirichlet problem well defined on a space with a boundary, I need to just be able to show that the variation vanishes every time I solve the equations of motion, which doesn't happen in this case, because the variation doesn't vanish when I solve the equations of motion. So I need to add something to the Einstein-Hilbert action in order to make the problem well defined. Oh, yeah, sorry, here. Yes, thank you. Okay. So it turns out that the thing to be added is nowadays called the Gibbons-Hawking-York term. So you need to add, in order to make the variational problem well defined, you need to add 1/8 pi integral over the boundary of k, which I'm going to define in a second, d3x. What is k? K is the trace of the extrinsic curvature of the surface. The extrinsic curvature of a surface measures how much the surface is curved inside the space that is embedded in. This is different from the intrinsic curvature, which is something that characterizes the geometry of the surface itself. The paradigmatic example is the cylinder. You take a piece of paper. When I give this lecture with a piece of paper rather than the iPad, I can actually turn the piece of paper. You take a piece of paper, it's flat, it's intrinsically flat. Then I fold it. I've not changed the geometry, I've not caused any crease or any singularity to happen. So the cylinder is intrinsically flat. It's just a flat space in itself. However, we all agree that when it's embedded in R3, when it's embedded in space, and this thing looks very much curved, right? So the extrinsic curvature of a cylinder is non-zero. Its intrinsic curvature is 0. So that's what the extrinsic curvature is measuring. You can show, it's shown in the lectures, in the notes, that another paradigmatic example is if you take as a surface, you take as a surface in your manifold, say, let's take the manifold to be R to some power, you take as a surface the level set of some function, and then you show from the definition of the extrinsic curvature, which I'm not giving you right now, but there is a way of computing it given any metric, that the extrinsic curvature is actually the projection of the second derivative of the function. So it's literally how the function deviates from being flat. F, so you take a point, you look at the expansion of the function near this point as an hypersurface, it's the level set. It's 0, then it's f prime is also 0 because we are at linear order and we are solving the equation, the level set. And then we look at how the paraboloid approximates the function. So we are literally looking at whether it's convex or concave. That's our intuitive sense of what is curvature. Formally, more generally, if you take a surface and you induce a metric on this surface from the embedding space metric, then KAB is the Lie derivative along the normal of the induced metric. Okay, this is a definition. It's not very useful for now, but it's very useful to compute the extrinsic curvature of the surface in all the space-time that we had considered earlier. So let's consider the case that I had introduced on Tuesday. So statically, spherically symmetric spacetimes. Now, the thing that we want to check, the thing that we are considering all these spacetimes, and we want to compute the action for spaces that fill this type of tubes. So we need to consider the boundary at fixed R, which is this boundary. This is our boundary sigma, or surface sigma. There is an induced metric, which is, sorry. And then we can compute the extrinsic curvature from its definition. Then we take the trace using the induced metric, and it turns out that this trace is this. Okay, why did I choose to show this? Is because this will be the fundamental ingredient of all the next computations. So I wanted to show you that you can compute it, even though I didn't tell you how to. But once you compute it, you see that it will depend crucially on f, which is the embedding function of the surface r is equal to r0 inside our spacetime. Okay, the importance for this term, once it's added to the Einstein-Hilbert action, is the fact that delta of S Einstein-Hilbert più S Gibbons-Hawking-York is equal to the integral over the entire manifold of the equations of motion delta GAB plus the integral over the boundary where this pi I, pi AB okay, so this is very different from this one in two ways. So the first one is that now I can set one special boundary condition, which is that I fix the induced metric on the boundary. So now I have a Dirichlet problem where I'm fixing the boundary condition just by fixing the induced metric. And then if I fix delta H, then the variational problem is well defined in the sense that corresponding to a variation of the action, I have to only solve the equations of motion. Or I can fix the derivative in a sense of the metric, which is this tensor here. And if I fix the derivative, why is it a derivative? Because K is a Lie derivative, so it's a derivative of the boundary metric. So I can either fix Dirichlet or Neumann boundary conditions, and in both cases, the variational problem is well defined. This tensor is called Brown-York stress tensor. And will return tomorrow. It's a measure of the energy inside the space. Okay, so now we assume that we have done everything correctly. We take the Einstein-Hilbert action plus the Gibbons-Hawking-York term. We fix the boundary condition on the metric. We fix the boundary metric induced on the boundary of our space. And we just need to solve the equations of motion. Once we find the equations of motion, once we find solutions to the equation of motion, we can actually compute this weight. Compute the weight of every configuration. Okay. Questions? Yes?
What's the problem that you just insert the Einstein-Hilbert action right away in the particular concept? You need to do all these calculations to take the equations of motion. Why you just can't take the action and compute the particular?
Because it's not well defined then. Because I have a boundary. So if you were to solve everything, if you have to solve the variational problem without a boundary, right? I mean, imagine that you're doing classical mechanics. You need to show that using in Hamilton's principles idea, you need to show that the classical solutions, so the solutions, the things that maximize the action, that extremize the action, are the solutions to the equations of motion. Right? That's the idea. Extremum corresponds to solutions to the equations of motion. But if I just take the Einstein-Hilbert action, then the extrema are not the solutions to the equations of motion, because I have this term that is non-zero, that can be non-zero. Right? So the extrema, so the things that extremize its variation, then are not just this. Whereas if I include the Gibbons-Hawking-York term, this is actually true. So I fix the boundary conditions, I can fix some boundary conditions, and then the extrema will be the solutions to the equations of motion. Therefore, when I do the next thing that I'm gonna do, 1 second, everything will be consistent. Other questions? Suppose, concretely, suppose you vary this, right? You will find some x dot, but you will also find an x prime at x at the an x prime at the two sides. This is the Dirichlet problem. Okay. So until now, I was working in Lorentzian, and I basically set up this definition up to here, right? So until now, we are setting up this definition, the Feynman's definition of the amplitudes. But now we would like to define the thing that I said was more rigorously constructed, the Feynman-Katz definition of the path integral. So I need to do a Wick rotation. I assume that that's possible, and that's one of the subtleties that tomorrow will come back to bite us. And I just take T2, so I do a Wick rotation, an analytic continuation. Formally, this means that I'm assuming that there exists a t everywhere defined, a coordinate t everywhere defined in my Lorentzian spacetime, and I'm analytically continuing to minus it, a Euclidean coordinate that is real. So I'm rotating the path integral contour. You could have problems with that, you would be right, and tomorrow we'll see some of the problems that happen there. The relation between the Euclideanized Einstein-Hilbert action and the Lorentzian Einstein-Hilbert action is exactly the same as the ones for the one-dimensional quantum mechanics. So, this is the Euclideanized action. NSGHI. Okay? Great. So now we are in the realm of Euclidean computations. But we have seen yesterday and just now that where Euclidean geometry really shines is when we consider thermal systems, because, I repeat it once again, Lorentzian on field theory sigma at temperature T is equivalent to Euclidean Q of T on sigma 1 beta times sigma, where so this is the expectation. This is what happens for Q of T. And we will see that this is the same property that gravity has, if you believe the computation that I'm going to do next. Tomorrow we will see that that's not technically really true, but with good approximation. Okay, so we start doing, if there are no complaints or comments or questions, I'll start with the computation. So we take the gravitational path integral seriously, and we want to consider a thermal state of gravity. So, to do so, we consider the path integral with boundary conditions, so-called thermal. So we consider the gravitational path integral over all the geometries that fill a space that is S1 times something. Vp over all m with, let's fix it to be the two-sphere, just because this way we can use that metric, that particular metric, okay? And the statement is that this is the partition function of this temperature, of this system. But really the canonical state function for a system, the state function in the canonical ensemble is the free energy. What's the relation between the free energy and the path and the z grav? Is beta fb right, where F is the free energy of my system. Now I will do some magic. I don't really know how to compute Z grav, because as I said before, it's not here anymore, but it's the integral over all the metrics with including all the fluctuations of the metric. This is not well-defined thing. So I'm going to do a saddle point approximation to this path integral, just like I can do, it was here, on the Feynman's path integral. The Feynman's path integral is dominated by the things that extremize the action, right? What are the things that extremize the action? the classical trajectories because of Hamilton's principle that I was mentioning earlier. So here I'll do the same, and since I have added the Gibbons-Hawking-York term, and this answers your question, I know that the saddle points, so the things that extremize the action, will also be the solutions to the equations of motion of my gravity, which would not be the case had I not added the Gibbons-Hawking-York term. Okay, so remember that Z I'm not, plus. So its logarithm is this object. But now in the semi-classical approximation, this is dominated by the Einstein, let me just call S Einstein-Hilbert plus Gibbons-Hawking-York term. Just, you know that it's there. So it's S evaluated on the solution to the equations of motion minus log, I don't even know how to write it, but S2. So I've done an expansion of S around the saddle point. Since it's a saddle point, the first order approximation vanishes because it's a saddle point, it solves the equations of motion. And so I'm left with the second order expansion, which I've called S2. Evaluated on G, sorry, I'm integrating, so it's evaluated. This thing, I'll call the one loop. I've done something wrong, I'm sorry. I set H bar to 1 in my head. This is because I've never set H bar different to 1 in my entire life, basically. But let's suppose that H bar is there. That's where H bar will appear. This is the one loop, and this is the classical term. Where classical here appears because it's an analogy with the Feynman's idea that they are the solution to the classical equations of motion. It's classical mechanics. So now I do the semi-classical approximation. I take H bar to 0 while keeping H bar beta fixed because it was literally here. This is TE by construction. So this is called the semi-classical approximation. In the semi-classical approximation, all these terms, all the corrections I can ignore, and this is the leading contribution. Therefore, I have the equation uguale a I, where this I've changed name, and I is the on-shell action evaluated on the solution. This equation is sufficiently surprising to deserve a name on its own, and we call it the quantum statistical relation. So it's quantum for obvious reason, because there is an H bar, which will be 1 from now on. And it's a statistical relation because there is an additional relation that you know in the canonical ensemble that relates the free energy to the other quantities that you can evaluate. Which is that F is equal to Ts minus B. I hope the signs are correct. No. So from this, we find, from these relations together, we find that we can study the thermodynamics of the gravitational system at a fixed temperature beta, so in the canonical ensemble, simply by computing the on-shell action of the gravitation of the configuration that dominates the ensemble, that we think dominates the ensemble. So we compute the on-shell action, we obtain the free energy from the left-hand side, and from the free energy we can obtain the energy and the entropy. Questions about this? Yes? Sorry? Sorry, the H bar? No. Oh, yes, yeah, I'm only doing semi-classical analysis. Then tomorrow, I'll tell you why the one loop screws the entire computation. I know, but the point, the surprising thing about this, the gravitational path integral, and it's the reason that we still believe it makes sense, is that we will see in a second that when you do this and you really think, this is what it should be, you obtain the right result. You obtain the right result that we had computed in Lorentzian, doing real, QFT on algebraic approach to QFT and doing the Bisonano-Wickman and computing things in a proper, rigorous way. Then we just do the semi-classical analysis and we find that it works. Not only that, you can also compute the quantum information content of the black hole. You can show that the page curve appears just by doing the semi-classical approximation to gravity and looking at all the saddles. So, yes, it's true that the one loop contribution screws up the computation, and it's true that there are so many subtleties everywhere. Why is T well defined? What happened? Still, it works. So we have to believe it. Okay. Other questions? Yes. Yes. It's a very good question. It's it's a very good question. It's something that I will try to tell you about tomorrow. In general, yes. So the answer is technically no, because temperature properly is only defined if you have an S1 overall in space-time. Whereas the space-time that will dominate the ensemble is the Schwarzschild black hole that doesn't have any S1. There is no circle there. So it's kind of a mystery where the entropy appears, and this will be one of the things to discuss tomorrow. But you could also wonder about something even more extreme than what you just said. So you could, until now, I'm doing things that have a Lorentzian interpretation, because I can invert that relation, that Wick rotation relation, and I can go back to something that has a well-defined time direction and some integral over something else, some S2. But you can also compute, and perhaps James later will tell you about this, the on-shell action for configurations that fill boundaries with arbitrary topologies, such as an S3, which is not even that weird. But there is no Lorentzian interpretation for field theory on S3, because there is no Lorentzian metric on S3. So this would be another feature that we'll be discussing tomorrow. Yeah, so we just, right now we follow our nose, and then it's subject to current research is working on this. Yes. Other questions? Okay, so let's look at an actual computation. Okay. I wrote there the Einstein-Hilbert action. The equations that follow from the Einstein-Hilbert action is this, but then I can do the trace reversion, so I can remove R from appearing explicitly. And in 4 dimension, it becomes this. These are equivalent. Then, this equation is the equation that defines the classical solutions. This equation is called, so the manifolds that satisfy this equation are called Einstein manifolds. This is just some nomenclature, but they have been studied at length because they are the canonical solutions to the equations of motion. There is an obvious case, which is the one that I mentioned in the past 2 days, where you take lambda is equal to 0. So we are doing gravity in flat space, in the sense that the vacuum solution, the simplest solution to this equation, is flat space. And the spherically symmetric black hole that is Ricci flat is the Schwarzschild solution. Oops. I should also tell you that flat doesn't mean trivial, right? So the Schwarzschild black hole has an horizon and has physics associated to it. You can also have the Kerr-Newman black hole. You can have a bunch of different solutions to lambda in the lambda is equal to 0 context that have very interesting physics. So it's still a very interesting case. However, it has a problem that makes the entire setup of the gravitational path integral even more debatable than it could be, which is that the temperature for the Schwarzschild black hole, so suppose I was to actually do this the computation that I said earlier, so we look at all the GPI over all the shadows with boundary S1 times S2, I tell you that the Schwarzschild is the dominant contribution, suppose. Then you compute the temperature of the Schwarzschild using whatever method you want, including the ones that we used earlier, and you find that the temperature is inversely proportional to the mass. But this is a problem because if you have a thermodynamical system in canonical space, you can compute the specific heat, which is the variation of the energy with respect to the temperature. The energy of Schwarzschild is its mass, which means that I invert this, so I have m is equal to 1 over 8 pi t, but then the derivative with respect to t gives me minus 1 over t squared. This is always negative, but something with negative specific heat is it cannot be in equilibrium. It's not a thermal state. It cannot be in a thermal equilibrium with a heat reservoir that fixes its temperature. The canonical ensemble is not Yes, so in 2 dimensions, for instance, in 2 dimension in ADS, you can actually compute the quantum, the one loop contribution. You can even solve it in full. With supersymmetry, there are also cases where you can solve the entire path integral. Yes, there are simplified settings where the gravitational path integral makes complete sense, in the sense that it's well defined even at the quantum level. But then you're not just studying Einstein-Hilbert action, you're studying a different theory. So in 2 dimensions, you're studying Jacques-Teitelbaum theory, for instance, or in 3 dimension is weirder. It's more subtle, even more subtle. But yeah, so far in 4 dimensions, there is no computation of the quantum path integral, unless you specify the geometry in a very special way. Okay, so rather than studying Schwarzschild, so rather than starting flat space, we look at ADS. So we'll set lambda to be minus 3 over L squared. The cosmological constant as measured as dimensions length to the minus 2. So we set L to be our unit length, our unit measure of length. And we normalize it to 3. You'll see it in a second why. The vacuum space that solves these equations is the constant curvature space, which is ADS, or actually, since we are in we are working in Euclidean, is also called the hyperbolic force space. It's constant curvature in the sense that its Riemann curvature is fully specified by its metric. Oh my God, CBC JT. This is not the case. This is not the case for Schwarzschild, for instance. So gravity here is trivial in the sense that you give me the metric, it specifies everything that will happen in gravity, all the geodesics, all the motion of particles and everything. This is not true if the space is not constant curvature. So sometimes I'll call it Euclidean ADS4, sometimes I'll call it H4, sometimes I'll call it ADS4. So these are all the same for the purposes of these lectures, but in the lecture note I make sure to differentiate between the two, between Lorentzian and Euclidean. But now 2 is 1 and pi is 1, you know, it's all the same. Okay, so there exists the possibility of writing a metric so there is a coordinate system that covers the entirety of the space. It's this coordinate system where T is TE and R is just a radial direction. R ranges over the entire real numbers. TE ranges over the entire real numbers. And this covers the entirety of hyperbolic space. Yes? Yes, so in Lorentzian, that's true. This is actually very important. I'll tell you in a second why that's very important. Yes, it's a feature. It's not a bad thing. It's a feature. Yes. So these are global coordinates on ADS in the sense that they cover the entirety of ADS. Sorry. And DE never vanishes. So there is no horizon. So the computation that we did earlier of about a Killing horizon, there is no horizon. The topology of of the space is the same as R4 in the sense that it's trivial topology. So R times R times R times S2, and this shrinks smoothly, so it's just R4. So it's technically it's R3 times R, which is R4. In order to do the path integral on this space, we need to do the picture that I had earlier. So we need to consider an M0 that is only the space between 0 and R0, where R0 is my cutoff, where I impose the boundary conditions. And then I consider ADS4 as one of the solutions that fills the boundary conditions. It's a solution of Einstein, that's the normalization. So if I use this normalization, then I'll find that it solves the Einstein's equation with this cosmological constant. L is also called the radius of ADS because it's a length, and for the sphere you would have the actual radius of the space. Okay, so what happens on R0? I have an induced metric, which is F. And near the boundary, this looks like, sorry, if I go for large R0, that's what I mean by near the boundary, plus L squared. Okay, so can I do the path integral on this space? Yes, provided I identify TE, because notice that this space has topology R times S2, whereas with an S2 of radius L squared, whereas I was starting with the requirement that the boundary needed to have topology S1. So I need to identify TE with TE plus beta. Notice that this beta is unspecified by the geometry. There is no need to specify a particular beta, to fix a particular beta by requiring some smoothness or something else, which will be the case in a second. So if I do this, then I have something that has a boundary S1 times S2. You should protest because this is not a real boundary, because R0 it diverges in length, but it's something that is called a conformal boundary. But for the purposes of this computation, it still works. So now we compute the on-shell action of this space. Do you agree that this is a good saddle of the gravitational path integral that I want to consider? I fixed the boundary condition. This is a solution to the Einstein's equation with the appropriate boundary condition. It's a good saddle that I should be able to compute its energy and so on. Okay, so you compute the on-shell action. You'll need to consider the Einstein-Hilbert. So when I take the on-shell action, I can substitute back in R minus 2 lambda the value of R, but the value of R is 4 lambda. So I can substitute it back. I'll get 4 lambda minus 2 lambda, which is 2 lambda, so it's just minus. Yeah, but lambda is minus 3 divided by 2 squared, so it's 1 divided by 16 pi integral of L divided by S squared okay, this is on shell. This is the bulk contribution, the Einstein-Hilbert contribution. This you compute, it's just an integral. You do the integral. You do the integral over TE, you'll get beta. You need the integral over S2, you'll get the volume of the S2. And then you'll need to do the integral over R, over the coordinate R. Where is it? Here. And this cancel out. So you just need to take the integral of this R squared, which gives you an R cube. So it's beta divided by 2L squared, R0 cubed. Okay. Now we need to compute the Gibbons-Hawking-York term, which is this one. Ah, fantastic. This was totally calculated. Obviously, I wanted to land here. In order to compute the Gibbons-Hawking... No, I canceled this one. Undo. What is it? 2 square root of f plus square root of f 2 divided by r. Okay. So I need to compute the Gibbons-Hawking-York term here. Notice that this depends. I need to choose what is the surface where I'm computing this, and this is the boundary at r is equal to r0. So it's just something that depends on r0, right? And then I have the volume. Cubed plus 2r0 L squared. So the final result is beta divided by 2g L squared minus 2r0 cubed minus 2r0L. In order to compute the on-shell action of the entire space, I will need to take r0 to infinity, because I was computing only in something finite. But then in order to compute the on-shell action of the entire space, I need to remove the cutoff. I need to take r0 to infinity. However, you see that this diverges if I take r0 to infinity. This I naught diverges if I take r0 to infinity. So this another magic of anti-de Sitter space is that, at least in pure gravity, there is a canonical way of removing these divergences. It's a process called holographic renormalization. I need to change the chalk. So if you do holographic renormalization, the idea is that whatever your original I naught, which diverges, so I can write it as I naught divergent plus I naught finite. Then the statement of holographic normalization is that there exists a combination of terms that only depends on the intrinsic geometry such that ICT, so it cancels perfectly, that's not true, plus something such that ICT plus I0 div equals finite. This technique, doing this technique is actually very technical, in the sense that you need to check what are the divergent terms. You need to be able to show that there exists a function of the intrinsic geometry, so a function of the induced metric, its curvatures, and possibly other terms that are finite, such that you cancel the divergence order by order. This is it's kind of a, well, okay, so it depends on your viewpoint, but it's either a miracle of ADS or it's the reason that ADS CFT works. You can also add matter fields, and you can show that this is still true, in all the cases that I know of. Okay, so in 4 dimension, the actual expression of the counter terms depends on the dimension. In 4 dimension, the statement is that this combination, where R is the Ricci scalar of the induced metric, cancels all the divergences that appear here. 4 ADS R0 cube plus something that is smaller, it's little o1 when I take R0 to infinity. See? That's cool. So the final result, I naught plus the counter terms, is 0. This is the action of ADS, of Euclidean ADS4. Even this is not technically correct, because it's only the action of ADS4 when I foliate it, when I consider it with boundary S1 times S2. There are other ways to foliate, to consider surfaces of constant R that give you different boundaries. For instance, this will be important for the talk later. The action of Euclidean ADS4, where you foliate it by S3s, is pi divided by 2. I have set G to 1. It's a fun computation that you can do. It's very easy. Okay. This was one solution to the equations of motion. There is questions about this computation? The steps are clear. I first compute the integral volume, then I do the Gibbon-Soking-York term, then I do the counter terms. I hope I have convinced you that it's a non-trivial computation, because that will be very important for this afternoon. There is another saddle that you can consider. So, meaning there is another solution that has the same boundary, conformal boundary, but it's different in the interior. It's ADS Schwarzschild. It has our favorite form. It's always the same. Notice that also ADS is the same. But now f of r is equal to 1 minus 2m divided by r plus r squared divided by l squared. Yes? Yes, I'll get there in literally 1 second. Well, okay, not literally 1 second, but close. Okay, so what can you observe of this geometry? First, when you take L to infinity, it goes to Schwarzschild, hence its name. It's a static space. It's spherically symmetric. When you Vic rotate it, so when you take TE to minus, when you go back to Lorentzian, you can show that the Lorentzian analog, brother, sorry, it has a gender because black hole in Italian is a male. Is it the same in Portuguese? Yeah, so it's a brother. Its Lorentzian brother has an horizon, has a Killing horizon for dt, which follows from the same computations that we did always and always, because there exists an R plus, there are many, but there exists at least an R plus, which is the largest root of f of r, such that f of r plus is 0, and f of r positive for r larger than r plus. So it has the same structure as our normal Killing horizon. Moreover, you can show that it's a Killing horizon, so that dt is normal to this surface, and you can compute the surface gravity. it's something. It's 1 divided by 4 pi r plus. Sorry, well, you can compute the temperature associated with this Killing horizon. 4 pi L squared. R plus is some function that solves this cubic. And moreover, there is a bifurcate surface. There is a bifurcation surface, which has the topology of S2. You can compute its area, and you can associate the entropy, the Bekenstein-Hawking entropy, pi r plus squared. Moreover, at r is equal to 0, there is a real coordinate singularity. You can compute the Kretschmann scalar and show that it diverges there. So, this is really a black hole. Okay? These are all Lorentzian computations. Questions about this? No. Good. So, now we'll do the Euclideanization of this space. When we do the Euclideanization, so when we consider this space as a solution to the saddle points, to the saddle equation, we need to make sure that we are summing over smooth spaces, because otherwise we need to include fantastic. I thought 5. Okay, so we need to make sure that we don't include singularities, simply because we don't know what to do at singularities. Until now, I've never told you what happens to gravity when I have a singularity. I've only considered smooth spaces. So we'll consider smooth spacetimes. What happens when we consider the smoothing of that space? So for all r larger than r plus, the space is smooth on its own. There is no problem. The metric is there, it's well defined, there's nothing. At r plus, there is a problem because f vanishes, and therefore one of the metric component divergence is divergent. So you need to make sure that everything is smooth there. So I'll do the canonical analysis that I did on Tuesday. So I define a geodesic coordinate near r plus. I look at the expansion in the geodesic coordinate, and I will find that the metric of the space is sorry, 0 squared. As I said on Tuesday, in order for this space to be smooth, I need the proper length of each circle. I realized that I need to make sure that this looks like the plane, like R2. So I need to identify this with an angle. But the only smooth structure on R2 is such that the proper length divided by the proper radius of each circle is 2 pi, which means that I need to make sure that the periodicity of TE is related to 2 pi. So I need to identify this such that beta okay. The resulting geometry overall is an R2 times S2, where the R2 has this, it's kind of like this. This doesn't work, but you know. It's like a cigar. It's something that opens up. This is R is equal to R plus. Here R goes to infinity. And the geometry opens up as r goes to infinity because the induced metric blows up in the same way that these blows up. And TE is the angular coordinate on this cigar. Okay? At each point of this cigar, over each point of this cigar, there is an S2 which just goes along for the ride. Okay? So notice this geometry is different from this topology, in which was the Lorentzian topology. Well, no, this was the Euclidean topology, but after this, it became this. So this is the obvious statement. This is different from this one. Also notice that while in ADS beta was unspecified, in ADS Schwarzschild beta is fixed by the geometry to be this because I'm requiring smoothness on the R2 factor, whereas there I just had a cylinder that continued. Okay, so I can study the induced metric on the surface of R is equal to R0. I can compute the on-shell action in the same sense, in the same way that I did earlier. So I can compute this on-shell action. The difference from before, sorry, I'll cheat. The difference from before is that R doesn't extend from 0 to R naught, but it only goes from R plus. So I have a finite contribution from the bulk term. The Gibbons-Hawking-York term is also different. It's different, I don't even, it's just a different thing. And, but then you can compute the counter terms. They add to the previous case. And the final result so here there is a non-trivial computation which is in the lecture notes. And the final result is that the action of ADS Schwarzschild is equal to beta divided by 4L squared, R plus L squared minus R plus squared. As R plus goes to 0, so if I remove the black hole, basically, this goes to 0, so I go to ADS. Okay, so let's do some physics with this. Questions about until here? Now I have two saddles that fill the same space. Okay, so the gravitational path integral says that I should sum, the prescription that I had somewhere was that I should sum overall the semi-classical contributions. This is a non-perturbative statement. The equivalent statement in field theory would be that I need to sum over the gauge field configuration with 0 curvature, but also over all the instantons. So in this sense, this is a non-perturbative statement. You will never find what I'm going to show now by doing perturbative quantization around the ADS. Okay, so first observation. Let's look at the temperature of ADS there, which is equivalent to beta, versus the temperature of Schwarzschild. The temperature of Schwarzschild, non-Schwarzschild ADS, real Schwarzschild, the flat space one, is 1 over 8 pi m, which is 1 over 2 pi r plus. So, I mean, it never gets there, right? That's the idea. This means that for any temperature, there exists a black hole. So I can fix any temperature, any beta at infinity, and I will find a black hole with that temperature. This is not true for ADS Schwarzschild. for ADS Schwarzschild, near R plus equal to 0, what is that? Near R plus is equal to 0, I have the same behavior as Schwarzschild, because the first term dominates over the second one. But at infinity, the second term dominates, and I have a linear behavior. So since I have two scales now, I have the cosmological constant and the mass of the black hole, R plus, I can play with them. So in particular, there exists a T min, which is square root of 3 times 2 pi L. Notice that again, as L goes to infinity, T min goes to 0, such that above T min, there are two black holes with the same temperature. Right? For all T above T min, I have this and I have this. These are both good black holes with different horizon radius. All the black holes that are on this branch are called the small black holes. All the black holes on this branch are called the large black holes, because R plus is smaller than the other. So, now I've showed that at fixed temperature, so in the canonical ensemble, there are really three saddles. There is ADS, ADS Schwarzschild small, ADS Schwarzschild large. So I need to compute the action of all these solutions. The action of ADS is just 0. And then I can compute the action of the large and the small black hole. If you do this computation, so you will say, I've already computed this action, but this action is expressed in the wrong variable because it's in R plus. Whereas I want to see what's the action in the canonical ensemble, so I need to invert the relation between T and R plus there, and I need to express the action in terms of the temperature. The result is this. This is a very famous graph, justly so. You have the contribution of ADS, which is just action 0, and then you have the contribution of the other two saddles. There is a T min. Before T min, there are no black holes. And then I have two branches of black holes, the small and the large. It turns out that the small black holes have always positive action. Whereas the large black holes, the large black holes have an action that goes like this. Well, technically it goes like this. Okay? These are the large ones. What does this mean in terms of our gravitational path integral? It means that we are fixing the boundary condition. So we are considering the thermal ensemble in a canonical ensemble, the thermal system in a canonical ensemble, so at fixed temperature. Below T minimum, the minimum temperature for the existence of the black hole, there is just a single saddle of ADS. There is ADS, there are particles around them. When I have T min, in principle I have a competition among three saddles. And I could have some phase transition between them. However, until I get to this point, which is, this is called the Hawking page temperature, until I get to the Hawking page temperature, ADS is always the dominant contribution. When I consider the gravitational path integral with a temperature that is larger than the Hawking page temperature, then the large black hole becomes the dominant contribution to my system. Therefore, I can expect, and I can compute the probability of this phase transition, a phase transition between ADS and the black hole. This is a non-perturbative phase transition in the sense that it's veiculated, I don't know, it happens via instantons, okay? It's a first order phase transition because because the energy is the free energy, which is I, is continuous, but its first derivative is not. And so you have what is called the Hawking-Page phase transition. Technically, it becomes a real phase transition only in the strict limit G to 0, because otherwise I should have considered the other contributions. This is amazing, by the way. I didn't hear that I was expecting, but this is amazing. This is something that we have computed just using the path integral. We have done a non-perturbative computation in gravity, just using semi-classical gravity. Moreover, and this answers your question about the Lorentzian, about the validity of this path integral. So first, you observe that beta here, so the thing that is required by regularity, is equivalent to 1 over t, but that was computed using the surface gravity, the kinematics of this system. Moreover, you can compute the energy of your system in the Schwarzschild ADS space. It turns out to be M. And you can compute S, the entropy, now not by computing the area of the horizon, but from its thermal definition. So as -1 plus beta d beta, the on-shell action. This definition follows from the fact that the entropy is beta squared, the derivative of the free energy, but once I insert the quantum statistical relation that relates the on-shell action to the free energy, it becomes this. You can compute this, and you find that it's pi r plus squared. This is the same thing that I had found in a completely different way from the Lorentzian computation. You can also compute the specific heat, and you can show that it's positive for the large black holes. For the small black hole, it's still negative. Okay, so this ends the physics part. Then you may wonder, why did ADS work better? Which answers your question. So it was not a second, but I got there at some point. So there are two intuitive reasons that you can believe or not. So the first one is that you remember that if you do the Newtonian approximation to GR, GTT should be, and I will get the signs wrong, but it's -1 plus phi minus phi. Well, the potential can be inferred from phi t. Sorry, I'll get the signs wrong here. But the gravitational potential in flat space was -2m over r. Whereas in ADS, there is so it's probably correct. Anyway, so in ADS, you'll see that at infinity, as r is above L squared, this dominates over this one, and it diverges like a parabola. Therefore, the ADS radius, the presence of the cosmological constant, acts like a potential well that confines gravity inside a box. This can be made precise in the sense that if you take the Penrose diagram of ADS, you'll see that it's periodic, well, and that massive particles are always inside the bulk. So the geodesics of massive particles are always inside the bulk, but the null geodesics get to the conformal boundary and back in a finite amount of time, which means that first it means that there is a communication between the conformal boundary and the bulk, but also means that it's still acting like a box, like the massive particles don't get there which is different from flat space. In fact, the fact that there is a communication with the conformal boundary is precisely what you were saying earlier. There is no Cauchy surface in ADS that would make the problem in Lorentzian space globally hyperbolic. Instead, the well-defined problem, as the Cauchy is time-like defined, the Cauchy surface is time-like. So in order to make the problem of quantization on ADS well-defined, I need to put boundary conditions on the time-like boundary. This is all hinting at the fact that if I fix the boundary, then I will see some back reaction in the bulk. And these, together with many other things, are the essential ingredients of the ADS-CFT correspondence, which says that gravity inside the bulk is fixed, is equivalent to a CFT at the boundary. Okay, I'm done. Thank you.
Thanks, Pietro, for such a lovely talk.
Thank you.
One quick question.
In this sense, the situation of the initial condition problem of ADS, that you need to impose the information on the time-like surface, it is alleviated because when we perform the Wick rotation, we are converting the hyperbolic equations into elliptic equations. So that we're only setting a sort of a boundary condition and everything is well defined when we perform all these schemes. Is that the spirit, let's say?
That's the spirit, but it's not the practice, in the sense that given a fixed conformal boundary, it's not true that the problem has a unique solution, or that it has a solution at all. So the non-uniqueness, I just showed you. I fix the conformal boundary as 1 times S2. There are 3 solutions that fill it. And there are many other cases where this doesn't happen. But even the existence is not obvious. It doesn't, it's not, generically it's not known that if you fix the conformal boundary, you will find a solution. Moreover, in recent times, but here I'm talking last year, people have suggested that this is the wrong problem at all. You should not look at the time-like boundary, but you should, with Dirichlet conditions fixed on the conformal boundary, but you should really look at a conformal class of metrics on this boundary, and this makes the problem completely as a different defined. So this is still work that is being done by not me, but people. It's really like last year stuff.
Thanks.
All right, we'll leave questions for you to ask later. Thanks again, Pietro.
Thank you.
To